Welcome to Module 7. In this module, we will talk about comparing two means using SPSS. This module covers Chapter 10 from your textbook. Here are the objectives of this module. So, in this module, we will talk about t-tests and we will cover different types of t-tests. And we will talk about the assumptions in order to choose what type of t-test we need to go with our data, and how to interpret the results, how to report the results, in other words, how to write up the results, and how to calculate an effect size. T-tests and ANOVA are inferential statistics. In other words, we can establish causality by conducting t-tests and ANOVA. Do you remember what's the difference between inferential statistics and descriptive statistics? So, in inferential statistics, we are inferring causality from our data set. But in descriptive statistics, we are just reporting the mean, median, mode, standard deviation, standard error, and etc. That's the main difference between inferential statistics and descriptive statistics. So t-tests and ANOVA are inferential statistics. We can establish causality here. So when we say t-tests or ANOVA, we are trying to find and determine the differences among groups or between groups. If we have two groups, we need to go with independent sample t-test or paired t-test. If if we have more than two groups, we have to go with ANOVA, which is a separate topic, and we will talk about that in next module. So, in order to determine the differences between groups, we have different statistical procedures to use. Um, Independent samples t-test and paired t-test. These are parametric statistics, which means we have to have established assumptions. We have to test for assumptions. And if those assumptions are met, we can go with independent samples t-test or paired t-test based on the nature of our data or based on the nature of our research question. And these tests, these t-tests and ANOVA, they have also non-parametric statistics versions. So in cases the assumptions are not met, then we can switch over to non-parametric statistics, including Mann-Whitney U-test, Wilcoxon-signed rank tests, Kruskal-Wallis test, and chi-square. So these are non-parametric versions of t-test and ANOVA. So as I said, we have to make sure that the assumptions are met. Otherwise, we have to go with non-parametric tests, statistic tests. So one of those assumptions is normal distribution. So we have to check for normality before conducting statistical analysis using t-test. So we can use Shapiro-Wilk test, we can use Kolmogorov-Smirnov test, we can use histogram, we can use QQ plot, PP plot, and there are different types of methods in order to determine the normality in the data set. So paired t-test or dependent t-test. So whenever we say t-test, paired t-test, it means dependent t-test. So here we are comparing the differences between pre and post test measurements. So for example, if our data from the same people measured at different times, we can use paired or dependent t-test. So let's say I want to measure total cholesterol at baseline and total cholesterol at uh, 6 months time point. So if I want to compare the mean of total cholesterol at baseline and at 6 month time point, I have to conduct paired or dependent t-test. Independent t-test. Here we have two independent groups, like male, female, BMI improved, BMI not improved, ill, healthy, um, cancer, not cancer, diabetes, not diabetes. So here I have two independent groups, and I want to compare the means of a variable across these two groups. In that case, I will conduct independent t-test. So as I said, in t-test and paired t-test and ANOVA, we can establish causality. So in other words, we can use these tests in experiments. So in experiments, we have two variables, independent variable and dependent variable. Independent variable is the variable we are manipulate, and we want to see what's the effect of that manipulation on the dependent variable. So I can go with that. I can use t-test or ANOVA here. So for example, is the movie Scream 2 scarier than the original Scream? We could measure heart rates. So my dependent variable is heart rates during both films and compare them. So I have one dependent variable here, which is heart rates, and one independent variable, which is the type of the film, the type of the movie, Scream 2 or Scream 1, or the original Scream. So in this situation, I need to analyze my data using t-test. So this is the example from your textbook, and we will get back to this. We will revisit this example later. So, but just for your information, we have 24 participants. I have 12 participants who were given an invisibility clock, and 12 participants were not given an invisibility clock. So the outcome is, so my outcome or my dependent variable is measuring how many mischievous acts participants performed in a week. That's my dependent variable. And my independent variable is those two groups, whether they were given invisibility clock or not given an invisibility clock. So I can put those data into a linear regression model, just what we did in previous module. So I'm just going to skip this. And I can get coefficients table if I use regression in SPSS. And it gives me T, which is kind of my t-test here. So the rationale for the t-tests. I have two samples, like male, female, diabetes, not diabetes, or sick, healthy, given invisibility clock or not given invisibility clock. Those are two different samples. Those are two independent samples which are collected and the means calculated. So those means can differ by either a little or a lot. So if my samples are coming from the same population, I would expect that those means are going to be similar, are going to be equal. So In null hypothesis, I would say there is no significant difference in the mean of two variables, of the mean of two groups. That will be my null hypothesis. And the alternate hypothesis will be there is a significant difference in the mean of variable dependent variable between two groups. That will be my alternative hypothesis. So let's say if I found a difference between the samples in terms of the mean of my dependent variable, I have two scenarios here. Whether there is no effect, but sample means from our population fluctuate a lot, and we happen to have collected two samples that produce very different means. I don't want that. We don't want that. The second scenario is what we want. The two samples come from different populations, which is why they have different means, and this difference is indicative of a genuine difference between the samples. In other words, the null hypothesis is unlikely. So, whenever I want to compare the mean of the dependent variable between two groups, I don't want to see a large fluctuation in the scores or in the values of the dependent variable in those two groups or those two samples. In those cases, my t-test will be incorrect, will be wrong. I just want my samples being dependent from each other. In other words, those two samples should come from different populations. And whenever I found a difference between the mean, I would assume that that difference is because of the different populations, not because of like a large and random fluctuation in the data set. I don't want that. So the larger the observed difference between the sample means, which is relative to the standard error, the more likely it is that the two sample means differ because of the different testing conditions imposed on each sample. As the observed difference between the sample means gets larger, the more confident we become that the second explanation is correct, which means the null hypothesis should be rejected. If the null hypothesis is incorrect, then we gain confidence that the two sample means differ because of the different experimental manipulation imposed on each sample. Therefore, we can establish causality here. How to calculate t? So in t-test, independent t-test, paired t-test, we get t statistic. And this is the formula. So you don't need to remember this formula. SPSS will do that for us. So t is observed difference between sample means minus expected difference between population means if null hypothesis is true divided by estimate of the standard error of the difference between two sample means. So this is the formula. So D is the observed difference between two sample means. And then mu is the difference in the population between two samples. And the divided by standard error. Standard error formula is standard deviation of the difference divided by the square root of sample size. So this is the formula for dependent t-test or the paired t-test. And this is the formula for independent t-test. So again, you don't have to memorize or remember this formula. So this is the independent t statistic formula, which is the mean of sample 1 minus the mean of sample 2 divided by the square root of standard deviation of each sample, or it is standard deviation. It's called pooled standard deviation. Let's talk about the assumptions of the t-test. So t-test has several assumptions, and we need to test for those assumptions before running the dependent or independent t-test. And the assumptions are a little bit similar between dependent and independent t-test, and those are parametric tests. So they assume a sampling distribution of the differences between scores to be normal, not the scores themselves. The data are measured at least at the interval level or ratio level. So if I have nominal or ordinal, I cannot use independent or paired t-test. We have to have homoscedasticity or homogeneity of variance, which means variances in those populations are roughly equal. And also I have to have an independence assumption. So scores in different treatment conditions are independent because they come from different people. So this is the assumptions for independent t-test. So in general, the assumptions are the means are normally distributed. Dependent variable is an interval or ratio measure, not ordinal or nominal. We have to have homogeneity of variance or homoscedasticity, which means we assume equal variance in both samples. And observations should be independent within each sample. T-test assumptions or t-test in general are robust to some violation of assumptions. But t-tests are not robust to between or within samples independence assumptions. And they are not robust to extreme violation of normality assumption unless in very large sample size. So we have to explore our data before performing a t-test. We have to check for outliers, normality, homogeneity, independence using different tests like box plots, histograms, descriptive statistics, PP plot, QQ plot, Shapiro-Wilk test, Kolmogorov-Smirnov test. And then if the assumptions are met, we can run the t-test. And later we can calculate the effect size. I'm going to skip this because I'm going to show you how to do that. Um, so this is what we will get if we run independent t-test. So remember, independent t-test is we have two different samples and we are comparing the sample means between those two samples. So that's why I have two samples here. I have no clock and clock. So I have sample size, mean, standard deviation um, for each group, and I have a statistic for that. I have 95% confidence interval as well. And this is what I will get from independent t-test output. So this is kind of descriptive statistics because I get mean and standard deviation for each sample. And remember, so I have two groups. I have group one is no clock and the group two is clock. And I want to compare the mean of my dependent variable between these two groups. This is the main table I will see from SPSS output window. So I have F statistic, the p-value for that, which shows the Levin's test or homoscedasticity assumption. I have T statistics, which is my t-test, and the degree of freedom, and then significance for one-sided significance or two-sided significance. Depending on our hypothesis, we can go with one-sided, but most of the time we look for two-sided significance or p-value. And also I get the mean difference, standard error difference, and 95% confidence interval of the difference. So look at this Levin's test column here. So Levin's test is for checking for homoscedasticity. The significance or p-value is 0.468, which means it is not significant. So the equal variance assumed here. So I have to read the t statistic degree of freedom. I need to look at the first row here. Let's say if this p-value for the Levin's test was less than 0.05, so I would assume that equal variance not assumed, then I will go with the second row and I would report that statistics there. So this is the reporting, but I'm gonna skip this because I'm gonna show you how to report the t-test results in APA format. So for independent t-test, we are testing for differences between means of two samples. Our dependent variable should be interval or ratio. It is useful when the sample size is small, and it is frequently misused because of its simplicity. It's very simple. And if we are running multiple independent t-tests in just one data set, we have to make Bonferroni correction. And this is kind of advanced statistics. I don't want to go into detail about that, but just for your information, whenever we are running multiple independent t-tests, we are inflating type 1 error. So we have to do some kind of correction to the p-value, and there is a formula to do that. So for example, the t-test can be used to test for a difference in test scores between a group of patients who were given a drug and a control group who received a placebo. So in that case, we will use independent t-test because I have two independent groups and I want to compare the mean value of test scores between those two groups. We can use t-test if the sample size are very small and samples are independent if study participants in one group are unrelated or different from those in the second group. Groups are independent if study subjects are randomly assigned to either the treatment or the control group. So how to do that in SPSS? We have to go to Analyze, Compare Means, and Independent Samples t-test. This is how we can do that. But there are different types of t-tests. We have one sample t-test. We have independent samples t-test, and we have paired sample t-test. One sample t-test is where I want to compare the mean value of my dependent variable to the mean value of that variable in the population. That's why it's called one sample t-test. So I have one sample and I want to compare the mean of that sample, the mean of the dependent variable in my sample, and compare it to the mean of that dependent variable in the population. Independent sample t-test is what we saw, and the paired sample t-test is comparing the mean value of dependent variable within subjects pre and post measurements. Bootstrapping, it's kind of advanced statistics, so I'm gonna skip this, but I just put it here for your information if you are interested in. I can calculate effect sizes, and these are two different effect sizes I can calculate. So I have a rho, and that's the formula, and I have D, and that's the formula for that. I'm gonna skip this one too. I'm gonna skip this one because I want to show you how to do that. Um, so this is an example for independent sample t-test. How can I develop my research question in independent sample t-test? I can say, is there a difference? Or I can say, is there a significant difference in dependent variable between group 1 and group 2? This is how I develop research question in independent sample t-test. So let's imagine I have my dependent variable is total cholesterol at a 6 month mark, and independent variable is BMI improved. So I have two groups, BMI improved or not. And I want to compare the mean of total cholesterol at 6 month mark between two groups. One is BMI improved and another one is BMI not improved. So what makes this an independent t-test? Because those whose BMI improved and those whose BMI did not improve are two separate groups with no overlap. In other words, they are independent from each other, not the same group at two different points in time that would make them dependent. So in order to analyze it, I will go to Analyze, Compare Means, and then I will choose Independent Samples t-test. The null hypothesis for independent t-test is the two population means are equal. That is my null hypothesis. The alternative hypothesis is the two population means are not equal. Or I can say the difference between the two population means is equal. That will be my null hypothesis. The alternative hypothesis, there are two ways to express alternative hypothesis in independent sample t-test. I can go with either the two population means are not equal or the difference between the two population means is not zero. So how to do that? So we need to go to the analyze and then compare means, and then we need to choose independent sample t-test. So the test variable is my dependent variable, and then grouping variable is BMI improved or BMI not improved. I'm gonna stop here and I'm gonna show you how to do that in SPSS. So this is my data set. This is this is a data set you will be using for this module assignment. So this is the variable view. I have total cholesterol at baseline, total cholesterol at I think this 3 months, and I have total cholesterol 6 month mark. And here I will have BMI improved or BMI not improved. This is here. So the label is 0 is not improvement, 1 is improvement. So I'm gonna go to analyze, compare means and independent samples t-test. So my test variable is total cholesterol um, at 6 months mark. My grouping variable is BMI improvement. So after moving the grouping variable, we have to define them. So group 1 is 0 and group 2 is 1 because of the labeling of the variable. I don't need to check any options here. I can also check the box estimate effect size and then click OK. So this is what I get. I have group statistics, which shows the mean and standard deviation, the sample size for each group, no improvement and improvement, and total cholesterol is my dependent variable. And I have dependent variable again here. I have Levin's test, which is kind of showing homoscedasticity or homogeneity of variance. The p-value is above zero point zero 0.05, so I would assume there is a there is an equal variance between two groups. So I will look at the first row. This is my t statistic. This is my degree of freedom. So degree of freedom is in an independent sample t-test. Degree of freedom is the total sample size, which is 133 plus 82. It is 215 minus 2 because I have two groups and it gives me 213. That's how SPSS gets degree of freedom. And this is my p-value, two-sided p-value, and then confidence interval. And this is the samples are independent samples effect sizes. So Cohen's d, these are different statistics, but Cohen's d and point estimate is 0.347, which is showing like a medium effect size. So let's go back to slide. So the significance column under the Levin's test for equality of variances gives us the value of 0.823, which is way above zero point zero 0.05. This tells us there is similar variability between the two groups. The significance column under t-test for equality of means gives us the value of 0.510, 510, so which is again way above zero point zero 0.05. So this means these results are not significant. So I would say there is not a significant difference between baseline marked total cholesterol levels in participants whose BMI improved versus participants whose BMI did not improve. So here I use total cholesterol at baseline, but the test I showed you in SPSS, that was total cholesterol at 6 months. So that's the difference. So I would say we failed to reject the null hypothesis. So this table, the bottom table, independent sample t-test, contains two sets of analysis, as I mentioned. So the first row assumes equal variances and the second does not. So to assess whether you should use the statistics for equal or unequal variances, use the significance level. associated with the value under the heading Leven's test for equality of variances. A small value in the column labeled significance indicates that this hypothesis is false and that the groups do indeed have unequal variance. But here the p-value is above 0.05, which indicates the hypothesis is correct and the groups have equal variance. So that's why I go with the first row. So this is how to report independent sample t-tests in APA style. So I would say an independent sample t-test was performed to evaluate whether there was a difference between the dependent variable of group 1 and group 2. The results indicated that there was no significant difference between the dependent variable of group 1, and then I report the mean value and standard deviation for group 1 and mean and standard deviation for group 2 had significantly higher or lower blah blah. And at the end, I would report T in parentheses, degree of freedom, and then I report the value of T and then P value. And I can get these values from these tables in SPSS. So remember, do not use brackets here, just use the parentheses. The non-parametric alternative for independent sample t-test is Mann-Whitney U-test. The assumption is the distribution may be normal or non-normal, and the dependent variable measured at interval or ratio or ordinal level. The second type of t-test is paired samples t-test. This is also known as dependent test or repeated measures t-test. So we have dependent variable here or test variable, which is a continuous variable, just like independent sample t-test. And we have some assumptions here as well. First assumption is the differences between paired scores are independent. Normal or approximately normal distribution of scores, dependent variable measure at the interval or ratio level. So the paired samples t-test is used to test the mean difference between two related measurements, such as pre and post. Or if we have twins or matched subjects. So for example, suppose managers at a fitness facility want to determine whether their weight loss program is effective. Because the before and after samples measure the same subjects, a paired t-test is the most appropriate analysis here. So the paired t-test or dependent t-test or repeated measures t-test calculates the difference within each subject, within each sample, before and after pair of measurements. It determines the mean of these changes and reports whether this mean of the difference is statistically significant. We shouldn't use paired sample t-test if we have unpaired data, comparisons between more than two units or groups, a continuous outcome, which is our dependent variable that is not normally distributed, and if we have ordinal or ranked dependent variable. But there are non-parametric version for paired sample t-test. So dependent variable should be a continuous variable. The paired measurements must be recorded in two separate variables. we have to have a related samples or groups, dependent observations. The subjects in each sample or group are the same. This means that the subjects in the first group are also in the second group because we are comparing pre and post. We have to have a random sample of data from the population. We have to have normal distribution of the difference between the paired values, not normal distribution of raw scores. We shouldn't have any outlier. So this is the hypothesis. So null hypothesis can be stated as the population mean of the differences equals the hypothesized mean of the differences. And the alternative hypothesis, so we have three different scenarios here. The population mean of the differences does not equal the hypothesized mean of the difference. Or we can say the population mean of the differences is greater than the hypothesized mean of the differences. Or the population mean of the differences is less than the hypothesized mean of the differences. So again, we are gonna use some kind of the same example, but the main difference here is the dependent variable is measured how many mischievous acts participants perform in week one and week two. So we have kind of pre and post, or we have two different time points here. I'm gonna skip this because I'm gonna show you how to do that. And this is the bootstrap. This is calculating effect size, but SPSS does that for us. And these are kind of advanced statistics. So for the paired sample t-test, my research question is I can write the research question like, is there a difference or is there a significant difference in dependent variable between time one and time two? This is how I develop research question in the paired sample t-test. So in the paired sample t-test, I have dependent variable, but I don't have independent variable. So I would say the variable one is total cholesterol at baseline. The variable two is total cholesterol at 6 months mark. And I'm just gonna compare the mean of the total cholesterol between these two time points. So how to do that? I would go to the analyze and then compare means. Then I choose paired sample t-test. And in this box, I have to move my variable. So I will move total cholesterol at baseline to variable one and total cholesterol at 6 month mark to variable two. And also I can check the estimate effect sizes. And then this will be my output. So the SPSS will provide statistics, descriptive statistics, including the sample size and the standard deviation and the mean for total cholesterol at baseline and total cholesterol at 6 months. It will also provide correlation and the paired sample t-test is the main table I will look for in SPSS output window. So here I get T, which is my t-test, the degree of freedom. So the degree of freedom is sample size minus one. So 200, because I have just one sample, right? I'm just comparing pre and post. So I'm using the same subjects. That's why the degree of freedom is sample size or n minus one. So 216 minus one is 215. And I will look for the two-sided p-value, and it is significant. And the effect size, I have Cohen's d here again, and that's my effect size. And this is how to report the paired sample t-test in APA format. Very similar to independent sample t-test. So you need to follow this in your write-up. And this is how we get these numbers from the tables in SPSS output. The non-parametric alternative for paired sample t-test is Wilcoxon signed rank test. The assumptions is very similar to Mann-Whitney U-test. So Mann-Whitney U-test is the non-parametric version for independent sample t-test. Wilcoxon signed rank test is the non-parametric version for paired sample t-test. For your assignment, the assignment for Module 7 has two parts, Part 1 and Part 2. In Part 1, you will find out if there is a difference in people who improved or did not improve their BMI based on the following: sedentary minutes, systolic blood pressure at 6 months or blood pressure 2, age, fruit, and vegetables. So you have four independent samples t-test analysis here for part one. But I don't want you to separate part one and part two in your assignment. Just put them beneath each other without mentioning part one or part two. So I want to see four separate independent samples t-test analysis in your assignment. And the part two is gonna be a paired sample t-test. So four paired sample t-test. Or three. So four independent sample t-test and three paired sample t-test. So I'm gonna quickly show you the paired sample t-test in SPSS. Um, let's see. Okay. Okay, so in order to the pair sample t-test, remember before running the t-test, independent sample t-test and pair sample t-test, you have to run assumption testing. And I want to see those in your assignment. I want to see the assumption testing in your assignment. So you have to do that. You have to test for assumption and then report the result for assumption and then do the independent sample t-test and pair sample t-test. Let's say if the assumptions are not met, for example, just report that the assumptions are not met but go with the independent sample t-test. I mean, go with the parametric version. I don't want to see non-parametric because we did that in previous module. So for paired sample t-test, I would go to analyze, compare means, and the paired samples t-test. So let's say I want to compare the mean value of systolic blood pressure um, systolic blood pressure in variable one. This is systolic blood pressure at baseline, and I have systolic blood pressure 2, which is kind of, let's assume it is 6 months mark. And I'm gonna move that to variable 2. I will check the estimate effect sizes and then standard deviation of the difference. Options, I don't have to do anything here and then click OK. So imagine I did assumption testing and I chose paired sample t-test. So the first table is the descriptive statistics, including the mean of systolic blood pressure at baseline and the mean of the systolic blood pressure at a 2 or 6 month mark, sample size. So this is the same number because I'm comparing pre and post. If I had any dropouts, I would have like, let's say 200 for second time point. but I don't have any dropouts, so it is the same. And I have standard deviation and standard error of the mean. I also have correlation between systolic blood pressure and at baseline and systolic blood pressure at two time point. The correlation is significant. And this is the main table. So I have systolic blood pressure at baseline minus systolic blood pressure at two because I'm comparing the mean. And this is the mean, the difference is standard deviation for that mean difference. I have 95% confidence interval for paired differences, and I have t statistic. This is my paired t-test, and degree of freedom, and then p-value. And the effect size here, I would go with Cohen's d, and then point estimate is 0.324. So, and I will write up the result using the template I provided.